We're going to continue our discussion on energy by introducing a new type of potential energy in the form of spring potential energy. We're also going to practice using the conservation of mechanical energy to solve problems in a way that's hopefully easier than using kinematics and forces. Those things have vectors in them, and vectors are complicated compared to energy because energy is just a scalar. That's really uh, part of what makes this mathematically easier, but we do have to have this intuition of energy conservation and how energy sort of transfers, changes shape from one form to another. And so that's going to be our objectives for today is uh, to use these conservation of mechanical energy in a practical sense to solve some problems and to introduce Hooke's law, which is the basis for how we understand springs. And let me just mention real quick with Hooke's law, right? So in future classes, you are going to, especially if you're an engineer, you're going to talk about how you manipulate objects or materials, how you can squeeze them and pull on them with tension, compression, or twist them. You're going to learn about you know, a Young's modulus and the bulk modulus and Poisson's ratio. Well, all this is related to Hooke's law, which is to say that, if you push on a spring, it wants to fight back. If you pull on a spring, it still wants to fight back. And materials in general, they like to go back to where their sort of rest state is, and how much they fight back is decided by something like a stress and strain curve. Hooke's law sort of deals in this regime, and so it's this sort of simple fight back system where the harder you push, the more you strain, uh, the harder it fights back or the more stress there is. Um, and so you will beat this to death in some sort of a higher engineering materials class or something. So this is not going to go away. Best to understand springs now. But first, let's talk about the potential energy and what we've learned so far, the gravitational potential, more specific. Last time we showed this equation that the uh, final potential energy plus the final kinetic is equal to the initial potential plus the initial kinetic. And so this is a conservation law, meaning that U plus K is conserved because U plus K initial equals U plus K final. And this worked when the way that we found this equation, well, we did this for free fall scenarios where something is just in the air. Uh, Maybe it's going up or down, it doesn't matter, but it's in the air and there's no other forces. But it turns out that we can show that this holds for all sorts of scenarios where you have something that goes up or down, even if it's connected to like a ramp like this, right? And if this thing goes down, this is very nice because we only need to look at the initial and the final state. This is say maybe well, okay, this one's going up, so this is the final, and this is the initial. We look at the initial kinetic energy and the initial uh, potential, and we compared that to the final kinetic and final potential, and they should be the same. These sums should be the same anyways. It'll even be path independent, meaning we can take this funky pathway to go up, and it still will sort of follow this equation. So we're gonna, yeah, using the same sort of process as before. If you recall, how did we even find that to begin with? We started with Newton's second law, F equals m dv dt, or sorry, dp dt. Nope, that's my mistake. No, it does equal m dv dt. Sorry, the m is already baked into the p. F equals dp dt. We moved around the dt, we did some calculus, and we ended up at this, initial and final after doing some integration from the initial state to the final state. So long as there was no friction and energy was conserved between the potential and kinetic, as we've written here. We can be more precise with our language a little bit later. It turned out, right? So we'll find that this is path independent, as I mentioned. That you can have these four scenarios, A, B, C, and D. And a lot of weird things happen, right? Like, so all of these are from the same height, meaning that they have the same initial potential energy. And if we drop them all from rest, then that means the initial kinetic energy is zero. And then they all hit the floor. You might be surprised to learn that because of that, they'll all have the same final velocity, since they must have the same final kinetic energy, since the initial potential energy is the same for all four scenarios. Regardless of this path, they'll all fall and hit the ground at the same speed. This only works with no friction. If there is friction, then essentially the longer your path, the more friction has time to sort of steal its energy from you. In this case, right, we could have done this with kinematics. You could figure out each of these cases. You can figure out like what's the normal force, what's gravity, what's this like leftover FGX doing some sort of a tilted axis. You don't want to do that if you don't have to. You could do that, looking for something like this. Well, oh, the normal force is changing over time. That's not fun. Uh, it's complicated, but you don't have to do any of it. We can skip right to the answer thanks to a conservation of energy. It turns out that since the normal force really is only there to change your direction and is not there to speed you up or slow you down in the long run, it is gravity that does that. And so the normal force won't really contribute to this kinetic energy. Same kind of thing happens with tension. Tension only changes your direction because it's pointing sort of towards the center of a big like circle. It's like a big centripetal force in some sense in something like this in a pendulum. Sorry, not tension in general. Tension in a pendulum. I should be specific. And uh, and so in something like this where you have a pendulum swinging, the tension will only change your direction, and gravity kind of does all of the work. And so both of these scenarios will fit with an equation like this, that the potential energy plus kinetic, just UG, gravitational, plus kinetic equals UGF, plus the final kinetic. So let's try one. Let's try a problem that may seem very daunting at first glance, but if we break it apart, each little individual piece is not that crazy of a problem to solve. So we have a 0.01 kilogram bullet. It lodges itself, meaning it stays within the block, onto a 1.2 kilogram wooden block and attached to a 1.5 meter long wire. The block plus bullet swings and is lifted until the wire forms a 40-degree angle compared to where it started. What is the speed of the original bullet? Okay, sounds like a doozy. We've got several little parts to this, many little values to worry about and contend with, but we can break it apart into two different problems by considering both the kinds of conservation that we talked about. So let's look, and we're going to actually start this one from the end and work backwards. If we see, like our final goal in this whole diagram is this value, the initial velocity of the bullet. Okay. Now what happened to that velocity? It lodged itself in here, and this thing went up. And so now we're here at the end. Look at the bullet, and we see we can ask about, well, either momentum or energy. The fact that it's sort of been lifted up by a small amount, let's call it delta y. That makes me think about the fact that it has increased in potential energy, UG, compared to this state over here, which you can call like the initial state of the second part of this action here. And so we can compare, right? When it reaches the top, it has this potential energy value, but it's reached the top. It's stopped moving up here. Therefore, we also know its kinetic energy would have to be zero at this point, the very end point. Um, that energy, that potential energy came from somewhere. Where did it come from? From here, from the bullet crashing into the wooden block. And so, in other words, if we find this potential final, that's going to help us find this kinetic energy initial, although really it's more like a kinetic in the median, not really the initial. And then this kinetic energy, how do we compare and find what happened with the bullet? Well, we can't do the same thing and look for a conservation of energy thing because there's no change in potential energy. There's no change in the height, and so we can't like get there using UG, and so kinetic energy initial equals kinetic energy final doesn't really mean much to us here, but what we can say is since if we have that middle point kinetic energy, if we have that K initial for step 2, I guess, or K final for step 1, then we could get that velocity, which for step 1, or for like the first half of this action here, this would be the final velocity of the wood plus block, and then you can imagine that the initial velocity of the bullet you may consider along with the initial velocity of the block in a conservation of momentum type way. So let's get solving here. Again, we'll start at the end. We're going to start at the potential and kinetic energy. So ignore this first part and look only. Let me do this in here. Look only in this part. This is like the second part of the action. We'll just write down something that's true. UGI plus KI equals UGF plus KF. That is, the initial potential plus initial kinetic is equal to final potential plus final kinetic. Look at the system and help me understand what are the different parts here. If we look at the initial potential energy, that's asking about this point in time. What's the potential energy? Well, we haven't quite yet decided how we're going to find y. In fact, let me first write down these equations, right? U is mgy, and k is 1/2 mv squared. These I don't require you to memorize anything, but I think you'll memorize that k is 1/2 mv squared against your will. U equals mga, y maybe, but I think the kinetic energy more so. But yeah, in this case, right, we may want to start deciding some axes, right? Say that this is the x direction, this is the y direction, and that perhaps the bottommost point of its trajectory we could say is y equals 0. It's probably a good idea. So anyways, we look at now knowing that this is y equals 0, we can say that the initial potential energy is going to be mg times 0, and so this goes away. And what about the initial kinetic energy? Well, I don't know the object's velocity. I don't know the velocity of the block plus bullet, but it's non-zero. So it is going to be 1/2 mv squared. I just want to treat that m carefully, for example. Now, what about the final? What about the final of this whole system here? Well, you see the little block plus bullet has swung this way. It has gained some height. It's gained a little bit of height. And we can figure out what that is. It's not as easy, but we can figure it out. And we have lost all of our kinetic energy, right? It's swung as high as it can, and therefore its velocity is 0. That's good. That means that the final kinetic energy is 0. Okay, so now we have pretty much part 1 of really solving things here. We've simplified our equation to be the initial kinetic equals the final potential, and this shows up so many times. This is very common, the way that the solutions to these problems go. But we do need to find, I guess the starting point here is to find UGF, okay? Because I have no way of knowing that initial velocity, but I do have a way of finding out the final y value, and that is by using the information given with respect to the rope, right? So the rope is 1.2 meters long, and then it goes to a 40-degree angle and is lifted in the air. You should be able to find using geometry. So let me draw a picture down here. Like this, 40 degrees, you should be able to find what this height is, delta y. And the drawing has given you a clue by drawing this triangle here for you. You know, at its longest point down here, it's 1.5 meters long, but up here, this sort of vertical part is L cosine of this angle, and so this is going to be, if this is L cos theta right here, and the whole thing is 1.5 meters, then the delta y that we're interested in is this value is 1.5 meters times 1.5 meters minus L cos theta, or L minus L cos theta is going to be our delta y value. And if you do that subtraction, so L is 1.5 meters, then you'll get, let's stick with purple here, that delta y equals 0.35 meters in the air. And so u is equal to, and let's keep this as variables for now, we'll just keep that value 0.35 meters. Mg, so actually let's be explicit here, UGF is equal to mgyf, and this should be equal to the initial kinetic energy, which in general is 1/2 mvi squared. If we solve for vi, right, so let me rewrite this, 1/2 mvi squared equals mgy f. We want to solve this for vi. You divide both sides by m. That's lucky, they cancel. And so vi, if you multiply both sides by 2 and take a square root, is equal to plus or minus the square root of 2g yf. Okay, well, the positive and negative is not actually going to be significant, but you can see from the picture that the initial velocity is to the right, so we should take the positive value, take the square root of 2 times 9.81 times the y we just found, 0.35. And I got 2.62 meters per second. You should do it yourself and corroborate. I'm not known to be the best at the calculator. But yeah, so this should be the initial velocity, not of the bullets, but of the bullet plus block system in the second half of this problem, this trajectory. Yeah, and this is complicated because that's going to change over time as it goes and travels upwards. It's going to slow down until it reaches 0 meters per second. But we don't care that much about the interim. We only care about these sort of critical points at the end and the beginning. We're going to take this forward. So this is the initial velocity of the block plus bullet. We're going to work backwards to find the velocity of just the bullet. So we know now that this value here is 2.62 meters per second. We're going to now look at this half of the problem, the beginning. And that's going to help us find the bullet. Because as we sort of decided earlier, this is going to be a conservation of momentum problem, right? So P, the sum of the initial P values as vectors is equal to the sum of the final P values as vectors. Vectors are not going to come too much into play since everything is to the right. No funny business happening with sort of, leftwards momentum. But it's good to just sort of keep them in mind. Now, if this is the initial state and this is the final state, then we can start plugging in things in. So the initial momentum is going to be the initial momentum of the bullet. I'll do with a BUL for bullet times the velocity initial of the bullet. And if we add that to M of the BLO, the block, times the V initial of the block, this should be equal to the final mass of the bullet plus block times the combined final bullet plus block, which we already have. That's the 2.62 meters per second. It's the combined. In the other case, it was the initial, but now it's the final velocity of this object. Now, this part is pretty nice. Look at this. What's the initial velocity of the block? Well, it's just dangling there, so its initial velocity is 0. That part cancels out, and so we're left with just mv of the initial bullet equals mv of the final bullet plus block, and we're looking for vi of the bullet. And so if we divide both sides by m, the mass of the bullet, we end up with, oops, so stray marks here. We end up with the right-hand side, the mass of the bullet plus block, times the velocity of final of the bullet plus block. Divide that by the mass of the bullet, and that would be our initial velocity of the bullet. So let's just mark what everything is. So this guy right here is going to be, I didn't need to cross it out. This guy right here is going to be, well, the combined mass of both. The bullet only weighs 0.01 kilograms, and the block weighs 1.2 kilograms, so 1.21 kilograms. And yes, this is 0.01 kilograms on the denominator, as I just mentioned. And this is going to be what we computed before, the 2.62 meters per second. Combine those together, and you get that the initial velocity of the bullet is 317.3 meters per second. And that was it. That was what the initial bullet was launched at. We ignored a few things like the fact that the bullet falls due to gravity. All this is sort of outside of our area of interest right now. We're really wanting to just see how we mesh together this change in gravitational potential with kinetic energy and the conservation of momentum. So yeah, hopefully this problem makes sense. I think this is the longest one of the bunch. So if you have any questions, rewind and stop and write down your questions for later. But we've got to move on. We've got to talk about we got to get to springs eventually. So in general, right, that problem was pretty good in that it showcases how we use like looking how we use that equation, the some of the potential and kinetic energies uh, to solve a problem. Together, we call this whole thing the U plus K. We just call that EMEC. EMEC is equal to U plus K, is the mechanical energy. Okay? And so in this scenario, we had a conservation of mechanical energy. But this isn't always true. This kind of energy isn't always conserved, or it's not always the same, because some of the energy can leave our system, right? This only works for an isolated system where no energy comes in or leaves, comes out of the system. Also, we are assuming that there's no sort of friction or no way of turning that mechanical energy into thermal energy uh, in order to use this conservation equation. Let's see an example where that kind of breaks down a little bit. So imagine we got two identical 1 kilogram clay balls flying towards each other. So like A is going to the right and B is coming to the left. And so they're all 1 kilogram. 1 kilogram is their mass. 1 kilogram mass. And they're both going at 10 meters per second. To keep in mind that the second one has a negative 10 meter per second velocity. So VB initial, I guess, is negative 10 meters per second. VA initial is 10 meters per second. They're going to come together, and since they're clay, they're going to stick. And so we're going to treat them just like the bullet plus block. It's going to stick and form one object. And what's their final velocity, right? So this is more of a conceptual one rather than a computing one, although you can compute. And also, what was their mechanical energy conserved? If you did the most recent lab, you kind of already know the answers here. So via the conservation of momentum in the initial state, we have a 1 kilogram block moving to the right at 10 meters per second, plus the other 1 kilogram block moving to the left at 10 meters per second. This is the sum of the initial momentum. It should be equal to a P final, the sum of P finals, really. And well, you see, you have plus and minus, the same thing, and this is going to be equal to 0. 0 is the sum of P final, and P final is really, since they stick together, it's really just going to be the mass of both together, so mass AB times VF. And so that means that VF is 0. It has to be in order for the final momentum to be 0. And doesn't that make sense, right? You slam two clay blocks towards each other. They're the same mass, same speed. They're going to smash together and form one little AB object. And it's just going to plop down on the ground with no velocity. Was their mechanical energy conserved? So just conceptually, look at so remember that the mechanical energy is kinetic plus potential. In this case, there's nothing to indicate potential energy, so we only need to worry about the 1/2 mv squared part. And you can add them together. The initial kinetic energy is going to be k of A plus k of B. And does the same thing happen? Do these velocities are going in opposite directions, so do they cancel? The answer is kind of no. The kinetic energies don't, because you square the velocity, and so 10 squared is 100, divided by 2 is 50, and so you have an initial Ka is 50 joules. Kb, well, you have negative 10 squared divided by 2 multiplied by 1 kilogram. That's also 50 joules. And so they both will provide 50 joules, in total 100 joules. In the initial state is going to be K total initial. But in the final state, well, they're not moving. And so therefore, they have no kinetic energy. K final is 0. Not the same as K initial. The mechanical energy was not conserved at all in this case. All right, let's move on to springs. So we've already talked about springs a little bit, and we've even mentioned Hooke's law and used it a little bit. So all this comes from Hooke and his famous little statement, ut tensio si quis. It's pretty much as the extension, so the force, is saying that the more you push or you pull on a spring, the more it wants to fight back. And so to formalize just a little bit, right, springs have a rest length. Sometimes I guess we call it X naught or L naught, where they don't apply any force. Any disturbance away from L naught, this rest length, will want to move it back towards L naught. And so it's a restoring force. Whether it's compressive, meaning you pull on the spring, or tensile, compressive means you push into the spring, or tensile, meaning you pull on the spring, it still will restore you back into the L knot. It will try its best in this F equals minus K delta X delta S sort of way. K is the spring constant. Be careful, that's a lowercase k, not kinetic energy. That's K, the spring constant, with units of newtons per meter. So again, not the kinetic energy. Right, L naught is the rest length. L is the current length. So delta S is how much we have stretched this spring by. And I use delta S, like it's delta X here because the spring is on its side. And by convention, we've decided that this is X and that's Y. But delta S is a generic uh, direction. We could have put this spring upwards or in some diagonal way. So delta S is just to indicate that it's in some direction. Okay. The negative sign comes from the restoring aspect that it sort of fights your whatever you do, it wants to fight that. Okay. And so K, the spring constant, is essentially a property of the spring. You can name the spring by its K value. I could say, look, this is my 20 Newton per meter spring. And that tells you pretty much everything you need to know just by saying what its K value is. In the same way that if I say I have a 50 kilogram block, you kind of know what that means, that the block's mass is 50 kilograms, and that may as well be the name of the block. We'll treat springs as massless, so they're not going to interact with their own sort of Newton's second law sort of things. This is the same way that we treated strings as massless for tension. Yeah, and so delta S can be generic. It can be up, down, left, or right. And so you do have to watch out for negative signs, I think, more than anything else when it comes to delta S. Let's just use that force real quick. Imagine that you have a bungee cord and it hangs and it's 30 meters long when nobody is on it. But after a person gets on it, then it stretches out, right? They do their jump and then it settles to a stop. And this 65 kilogram person has now caused this to stretch into 72 meters long, this bungee cord or bungee rope. Now, what is the elastic constant of the bungee rope? Well, uh, 30 meters is the length when nobody is on it, so we can treat this to be equal to our L naught, or our rest length. And so if we just write down, well, actually what we should be doing here is looking at our 65 kilograms and thinking about forces, right? This is applying a gravitational force, which is counteracted by our spring. And so just writing down Newton's second law, right, and in the y direction, the sum of the y forces has to be MAY. In this case, right, it's settled to a stop, and so this right-hand side is 0. The acceleration must be 0. And so we can see that Fs minus, right, because these are vectors, Fg is equal to 0. This is the left-hand side of Newton's second law, is Fs minus Fg. So Fs, Hooke's law says that this is, and now we do have to be careful, right? It's minus k delta S, but you kind of already know what direction the force is. It's upwards, so this should be a positive in the y direction. So it's going to be k times, and yeah, you can put a minus and then put a delta. It becomes very unclear what to do with the minus signs, but think of this as a whole, and it will be easier that way. If you put in, well, delta S would be 72 meters minus 30 meters. This entire force better be pointing in the positive y direction, and we see that that will give us a positive number, since k is always a positive number, and so this makes sense here. If g is going to be, well, the mass times gravity, mass times, oops, not 30. The mass is 65 kilograms. times 9.8 and meters per second squared, and this is going to be equal to 0. Yeah, if you solve for k, so you would add this, add it over there, and then divide out this 72 minus 30, or 42 meters. You will get that k is equal to 15.2 newtons per meter. So there's a very loose spring of low elasticity, which makes sense for a bungee cord. So yeah, I think the one part that might be confusing is the negative sign on the F equals minus K delta X equation. Uh, you you know you can be very formal about it and say, look, this is my delta means final minus initial. This is my initial position and this is my final. And say, well, if you take this to be 0, for example, then really this should be negative 72, negative 30, and start from there and put that in. But I think it's easier just to realize that the spring force, the way that we have drawn our force diagram, has to be positive, and so we make the the whole thing is going to be positive when you put in your delta S in this way. So, unlike previous forces, like springs can be a little bit more complicated because the spring force is inherently variable. As you move through the spring, you push and pull, it changes how strong it pushes and it pulls. And so as your kinematics evolve, uh, your force will evolve as well. But sometimes we're only interested in the before and after and not in the in between at all. And so that's a good time to look at energies instead of looking at Hooke's law. We can look at energies instead. Imagine a spring, right? So we talked about having potential energy with a bowling ball. You hold it up in the air and you sort of get a little bit anxious because it has so much potential energy. A compressed spring is the same way, or a spring under tension. They're storing energy. They have potential to be released. And so we have the spring potential energy that we'll see, but we need to do the math to get there. Uh, and when you see a slide like this, I would ask that you not get too scared, right? So we are all, uh, you know, engineers and physicists. We all sort of have to be mathematicians as well. So try to slowly follow along in the steps to see how we can find the spring potential energy. So we start with F equals ma, a very base, starting point. Um, and all that we're going to do is we're going to say, well, first A is dv dt, right? And so we can just replace this A with dv dt. We're going to say, well, the force that we have is coming from Hooke's law. Our force is going to be negative k delta x. Uh, just keep things in the x direction for no reason, just to make it a little bit easier. This next step is a little bit strange. This is the chain rule acting on dv dt. And we did this before when we found the conservation of energy. If v is a function of x and x is a function of t, then dv dt is dv dx dx dt. And so this is the chain rule being activated where we don't really have a function v of x, but we're doing it generically. Well, dx dt, that's just the velocity, right? Dx dt is just the velocity, so we can replace dx dt with vx. And now we can separate our variables and do some integration from the initial to the final state, right? We'll get this dx and move it over here. Uh, you know, uh, Mathematicians hate this one trick, just moving the dx, multiplying both sides by dx, and integrating. But we we sort of can do that and integrate from the initial velocity to the final, or the initial position to the final. And if we do that integral, right, what's the integral of mv? We already did that one before. That's 1/2 mv squared, kinetic energy. But what about this one? The integral of negative k times x minus xe in parentheses. Try this integral out. What's the technique? A little bit of a u substitution. Make your u value be equal to this. And we have the same exact integral, actually, negative k times x minus xe squared. Oops, I did forget a half. And so we see that integral here. It's just minus 1/2 kx squared. And so that's what this step is. If we plug in the x final and x initial, well, this equations become very long, right? This is the x final minus xe squared, and this is x initial minus xe squared. But why don't we separate out the finals minus initials? And when we have xf minus xe, a little bit easier just to call it delta x, just like we had delta s earlier. And so that's all I did in this step. Just rewrite it with delta x. And then we separate out. We put all the finals on one side and all the initials on the other. And look at what we have. 1/2 mvf squared. That sounds like the kinetic energy. Plus 1/2 k delta xf squared equals 1/2 mvi squared plus 1/2 k delta I squared. So we have the same exact formula, 1/2 mv squared plus 1/2 k delta x squared on both sides. Same exact formula, except one is all initials and one is all finals. And so that's how we can say we have a conserved quantity. And so this is always the same. This is always the same, so that is conserved. And really, it's just once again the same kind of thing. Kinetic plus potential is conserved. We now call this thing, this potential, the spring potential energy, 1/2 k delta S squared. So that's how we come up with a formula based on Hooke's law. We get down to the potential energy. And this is like the elastic potential energy. This is how much energy is stored in a spring. If you have a spring and you compress it, you compress it by like 1 centimeter. You can put in 1 centimeter for there and put in the spring constant for K, and you'll find a joule value for how much energy is stored in that spring. Let's do a problem. And we have one more problem after this, but we'll probably leave that for later. Let's do a problem in which we use this fact to bypass a lot of difficulties that would come from trying to tackle this with forces and kinematics. So we have a little spring-loaded gun, a lot like one of our earlier labs, and it has a 10-gram pellet that it's fired at an unknown speed. Okay, so we don't know what speed this is, but initially it was compressed by 10 centimeters, compressed by 10 centimeters uh, in by in a 10 Newton per meter spring. So this guy has a K value of 10 newtons per meter, which is what we've written here, and we've compressed it by 10 centimeters into its beyond its equilibrium length. And so this is nice because we have two parts. We have an initial and a final. An initial and a final. And we only need to worry about those. We don't want to compute Hooke's law because this is going to change over time as the spring applies its force on the ball and it flies. You would have to do Hooke's law, which over time you would have to figure out some really crazy kinematics to figure out what this final velocity is. Uh, I don't actually know how crazy it is. I rely on the energy instead because it's so much easier. Uh, well, K initial plus U initial is equal to K final plus U final. Look at the spring, the potential energy at the end. Well, in the initial it's compressed, but at the end it's expressed to its final L naught. So it is at rest. And so that means UF is 0. Right, so essentially 1/2 K delta S squared is 0 because delta S equals 0. It's at its equilibrium length. Conversely, the initial kinetic energy before we launched, it's not moving. It's not moving, so kinetic energy initial is 0, since 1/2 mvi squared is 0 because the v is 0. So once again, we have this scenario where we end up with ui equals kf, and we just have to plug things in. 1/2 k delta s, or delta x, delta whatever you want to call it, squared is equal to 1/2 mv f squared. I do want this to be an SI, as in an initial compression. So we're looking for the final velocity. All we have got to do is solve for VF. If we multiply both sides by 2, these 1/2s cancel, and then we can divide both sides by m, and we have VF squared equals k over m times delta S squared, delta Si. And if we square root both sides, then we end up with the final VF is equal to root k over m times delta Si. I guess technically we do have a plus or minus, but looking at the picture, we can see that this is going to be a rightwards velocity. We lose information about direction when we go with energy, because energy doesn't really have directionality to it. It's not a vector. K is 10 newtons per meter. M, the mass, is the 10 grams. So K is 10 newtons per meter. M is 10 grams, or 0.01 kilograms. And delta Si is the initial compression, which is the 10 centimeters, or 0.1 meters. And you can plug these in. I got about, I think, 0.3, maybe 0.32 meters per second as the final velocity of this little spring-loaded cannon. Yeah, so this is a same kind of problem as earlier, where we go from potential to kinetic, and this time we just have a spring potential, a different formula, but the same sort of overarching theme of looking for these changes in the energy. It's not always going to be so nice that the potential and kinetic go away, but there's always going to be a way to find them using the formulas in these problems. All right, so here is the last problem, which I'm going to set up for you, but I want you to try it on your own. And so here, it's a similar idea. We've got a trampoline that we're designing, and we want to consider an extreme case, right, where we have 200 kilograms worth of people lifted up 1.8 meters in the air above the trampoline. And when they land, they're going to squish and compress the trampoline down, right? And so we want to make sure that the way we build our trampoline, it's tall enough to where they squish and they won't touch the floor, or else they would hurt themselves on the floor below. The trampoline's material is elastic, and it has a K value. It has a K of K being the spring constant, not the kinetic energy, of 8,200 newtons per meter. And so how high above the floor should we build that trampoline so that they don't slam onto the floor? This was pretty tough. I think you want to make sure that you are explicit about where your origin is, and I think I would choose my origin to be here, below delta y. And if you think about what your initial, so what's going to happen here is we are going to have the energy, the mechanical energy Ui plus Ki equals UF plus KF. Uh, think about the kinetic energy at the top of the launch here. Look at that as at the top before they fall, and at the end when they're at the very bottom, it's actually going to be zero both times. The kinetic energy will be zero, but we're going to have two types of energies to contend with: the initial spring potential energy, and the initial gravitational potential energy, as well as the final. Okay. Be careful about what that y value is in the potential energy, right? It's not going to just be 1.8 meters. We're going to have to add delta y to it. So these are my little hints. Why don't you give this a shot, and then we can work through it together, or you can just cheat and look at the back of the notes since they are right here after your checklist of what you want to make sure that you understand. You can look through and look for the answer at the back. All right, I will see you all in class on Wednesday. See you there, folks.